Hi class, good day to you. This is our continuation of the lectures on quantum mechanics. Our reference is Introduction to Quantum Mechanics by David J. Griffiths. You can use any edition of this book, and I recommend you to buy this book. So what have we studied in the previous meeting? Um, we know that in quantum mechanics, QM, a system or a particle or system of particles always a wave function that is a function of space and time, and it is determined through the Schrodinger equation. And this is just a Schrodinger equation, which is just I h bar times the partial derivative of the wave function with respect to time. This is just equal to negative h bar square over 2m times the second order partial derivative of psi with respect to x square or space. It's the product of the potential times psi. According to Born's statistical interpretation, the modulus of psi square gives the probability density of finding the particle at point x at time t. This modulus is equivalent to the conjugate of psi times psi, or psi times its conjugate. In quantum mechanics also, the outcome of an experiment to measure a position is not predicted with certainty. However, or rather, QM or quantum mechanics only offers statistical information about the possible results. Here you have the modulus square of times dx is equal to the probability of between x plus dx. I say it again, probability of finding the particle between x and x plus dx at time t. On probability, we discussed about an example where students or in a room where there are people of different ages, and we made some statistical calculations there, and some of these formulas. This is just the total number. This is equation 1.4. The total number of particular elements characterized by some j's in a discrete sample is just equal to this n, which is equal to the summation of nj, where j comes from 0 to infinity. The j here could be the age or any characteristics of a sample. For example, the weight, for example, the height, the age, the grade, for example. So whatever it is that is an important characteristic would be placed in J. The average value of J, or the expectation value, this is just denoted by this symbol. You have a bracket, and in between those brackets, you have J. This is the expectation value. This is given by the summation over n. Or this is just also equal to summation of J times Pj, the probability of occurrence of that J. So J comes from, again, 0 until infinity. In general, any function of J that could be like e to the J plus square root of J, you can get the expectation value also by using this formula. If you want to get the average value of the function, then that function should be inside the times the probability of occurrence. We also learned about standard deviation, and the standard deviation is just equal to this. This is just equal to the average of the square of j minus the square of the average of j. And then the probability density, we also discussed that. Here, this is the probability density rho x times dx is the probability that individual chosen at random lies between x and x plus dx. So if you want to integrate from a certain position A to a later position B, then that's the probability of that individual chosen at random lying between A and B. So this is just, you just have to get the integral of this. So the probability x lies between A and B is given by this integral. For continuous the distribution, we have deduced these rules. No? The integral of the probability density dx taken from negative infinity to positive infinity is equal to 1. It's always equal to 1. And the expectation value of x is just the integral from negative infinity to positive infinity of x times the probability density times dx. Have a function, you can get also the expectation value of that through this integral. And the standard deviation is also calculated through this expression. In continuous distributions, we use integration rather than summation. So you have this integral. And to be able to integrate, you must review your integration course, and then that would be easy in the next in the later topics of these lectures. So we now go to normalization. If you have a Schrodinger equation, then that Schrodinger equation subjected to some initial conditions, you can find or you can determine the wave functions. And from the wave functions, if you get the modulus of that square, you can get the probability density of the system that you are interested, no? And this is, if you integrate this from negative infinity to positive infinity, according to Max Born, the integral of that is just, or is supposed to be equal to 1. So this is the probability density dx in place of the rho x here. This is a probability density, but in quantum mechanics, the wave function square is also the probability density. So that is why you have the integral of this times dx is equal to 1. However, there are requirements to this. There is a requirement to the wave function. The wave function must be normalizable. What is that? So let's talk about that later. And the wave function must go to 0 faster than 1 over square root of x as x approaches infinity, meaning that the wave function as it goes infinity, going from here, it should go down to 0 as it goes to the positive infinity. And if it goes to negative infinity, it should go like down to 0 to the negative infinity. That's the requirement for the wave function. So again, the wave function is coming from the Schrodinger equation, and the wave function is a solution to the Schrodinger equation. Let's look at the Schrodinger equation again. Here is the Schrodinger equation, and you'll be able to get this subject to some potential or constraints. And the Schrodinger equation would have a solution of psi, but the psi times to any constant a, where a is a complex number, is also a solution to the Schrodinger equation because so you can find a such that when you put the a here, a square, in this equation, you will be able to uh, find that a such that um, the the integral of the wave function is equal to 1. So if psi is not normalized, meaning if you only put psi here and the integral is not equal to 1, then you must multiply a constant here, a complex constant, a square. And if you look for that formula, because a is the normalizing factor of the wave function. So that process you were doing of finding a is called normalization. But there are also solutions of Schrodinger equation um, that are equal to 0. This is trivial solution to the Schrodinger equation. This is, of course, always a solution to the Schrodinger equation. And there are also solutions whose integrals are infinite, not 1. So in this case, it's infinite here, not equal to 1, or equal to 0 if psi is equal to 0. So if this is equal to infinity or 0 and not 1, then those wave functions are non-normal. Those wave functions are non-normalizable, and they cannot represent a system. They also cannot represent a particle or a system of particles. So we should reject those wave functions. Oh, we only accept those wave functions that are square integrable. Square integrable solutions to the Schrodinger equation. Those are the wave functions that represent physically realizable state. So those are the wave functions that you only consider. Um, if if you do this and it gives an infinity or 0, then forget about that wave function because those are not normalizable. So, by the way, some wave functions have phase or angular part in the wave function. Wave function is like this. You have is like a wave, and the wave is caused by some phase part. So if you look at some example of a wave function, like this, for example, this is the phase part of the wave function, but this is not significant if you calculate the, because that will cancel in the conjugate. So the phase is, this has no physical significance. So once a wave function is normalized, it stays normalized forever. The Schrodinger equation has the property that when a wave function is normalized, again, I'd like to tell you that the wave function comes from the Schrodinger equation. Once it is normalized for as long as it exists, and we should be able to prove that. And as we go through the slides, we'll see why is it preserved. So how do you preserve a wave function? So if the wave function is preserved for a certain time, then the derivative, I mean preserved with respect to time, that wave function should be, the derivative of that wave function with respect to time should be equal to 0. So in this case, we start with this. We have this wave function. The psi is the wave function. Let's look at this. If we get the derivative of this with respect to time, if this is equal to 0, then the wave normalized and preserved for all time. So we do this operation, derivative of the integral of psi squared dx. The derivative here, once it goes inside the integral, becomes a partial derivative. Why? This is a partial derivative because psi is a function of both space and time. So these are multivariable. So you have to use partial differential. So because position and t will be time, so partial differential is used. By product rule, this one, this quantity here, by product rule, this is this quantity. This one is equivalent to this one. So by product rule, by the way, this modulus of psi square is just equal to psi star psi, or psi asterisk psi. Then if you get the derivative of this, you should be doing this. You should write the first function here, derivative with respect to time of the second, plus the partial derivative of the first with respect to time times the second wave function. So that's the product rule of doing derivatives. So going back to the Schrodinger equation, this is the Schrodinger equation, equation 1.1, IH bar partial of psi with respect to t is equal to negative h bar square over 2m, second order partial derivative of psi with respect to x square plus the product of potential times psi. You can transform this by dividing with h bar, IH bar. So it becomes this. So you have h bar square divided by 2m divided by IH bar. The h bar will cancel, and then you have an I at the bottom. But if you transfer the I at the bottom to the top, you will change the sign. you have done um, complex number course, so you know why this becomes positive. And then here you have IH bar. So if you divide this by IH bar, you have IH bar here. So again, if you transfer the I to the top, like what happens here, it becomes negative. So this is still the Schrodinger's equation, just transformed. And if you get the complex conjugate of this, you just change the I to negative I. Complex conjugate of this is just equal to negative IH bar over 2m partial of psi star. Now the conjugate of psi o with respect to x squared plus the I here becomes negative I, so it becomes positive here. So you have I over h bar times the potential times psi star. So you now have an expression, this one for here and this one for here. So you can replace those expression by this expression by 1.24. So now after doing that, after replacing this expression with what we found, 1.23 and 1.24, we can rewrite the partial of psi squared with respect to time into this expression. It is now a partial derivative with respect to space. Here it is with respect to time. And this one is a partial derivative with respect to space. So you can manipulate them and you will arrive at this expression. The integral is now equal to the integral of this one, the integral of this function. This is just equal to, if you put the integral to the integral here. So you get the integral of this, and you will get, so this is supposed to be multiplied with dx. But the dx here, when you put the integral, the dx in this part will cancel with this. And so you will be left with the integral of the derivative of this one. So any integral of a derivative is just that function. So you will be left with this. So you will be left with this function, and you evaluate it from negative infinity to positive infinity. So now we had a condition for the wave function that at negative infinity or positive infinity, this psi star are 0. So at negative infinity, this is 0. So everything will be 0. And this is also 0. So everything will be 0. And at positive infinity, this will be 0. And this also will be 0. So everything will be 0. Therefore, the derivative with respect to time of this is equal to 0, meaning that the wave function is preserved in time. So if you have normalized this already, it's forever because it's preserved in time. So the derivative of this with respect to time is 0. It doesn't change over time. If psi is normalized at t equals 0, it stays normalized at all future times. So this is now the problem that you're going to do in your home. So you have this at particle t equal to 0. Um, you have a representing the particle where capital A and B are constants. So you'll do this instructions from A to F. You can try it at home, um, uh, doing that for this particular wave function. And then you also have another wave function here, 1.8, problem 1.8. This one is a little complicated because you have a and then you have also have a phase factor here. So you can then normalize the psi, determine the expectation values of x and of x squared, and do the instructions here. Maybe you could ask me in our forum at Mole, or at our Mole classroom, and in, also in our Google room for some clarifications regarding the problems. And also there's another problem here, um, where there's a derivative. Let's look at PAV. Where is that? PAV is this one with the rho x is being replaced by the modulus of psi square. So you can also do this. These are actually very easy, but you just have to spend time calculating them. So this is the derivative of that expression, and this is just equal to that, where this is the called the J. This is called the probability current, the JXT. And then you also have this problem. Just take time to read this, and then you can clarify this problem to me in our Google Classroom or Only Classroom. I am posting also this lecture there, so you can review the lecture. Now we go to um, momentum. In quantum mechanics, we have position, we have momentum, but there's no such thing as velocity in um, quantum mechanics. As you can see, very small particles in quantum mechanics, and those particles at their place in quantum mechanics, they are vibrating. At the point that they are actually not um, at they have no place. I mean, in space, they don't have a place. They are somewhere vibrating in that space. Quantum mechanics, classical mechanics can say that a particle is at this point, but quantum mechanics, yes, the particle is at that point, but it's only at that point. It's not certain in quantum mechanics, because at that point the particle is vibrating. That very small particle is vibrating. Remember that in quantum mechanics we're dealing with very small particles. We're not looking at particles that are very big. Quantum mechanics only applies to small particles, vibrating particles. That's why they have no certain position, and therefore they don't have certain velocities. But probable position, and then you also have a probable momentum for that associated with that. So for a particle in state psi, the expectation value is this one. So this is the probability density, as you can see, as we can look in the previous slides. This is the expectation value, but the rho, the probability density, is now replaced with the modulus of psi square. This. We have this expression. But what does this mean exactly? What is the meaning of this? This is expectation value of the position, but what is it really? So expectation value, this one, bracket x, bracketed x, is the average of the measurements performed on many or ensemble of particles with the same state psi. It's not just one system. You have an of identical systems that you are measuring only once. You're measuring only once, because if you measure them, that will affect their wave function after the measurement. The wave function of the particle after the measurement will not be the same as the wave function before the measurement. So you have to set up, for example, 1 million particles of the same state and simultaneously, and then you'll be able to get uh, this expectation value. So this one does not mean measurement of just one particle. This does not mean measurement of just one particle a large number of times. So you don't have one particle and then you measure it like 1 million times. It should be 1 million at one time, each of them, not one particle measured 1 million times, because that will lead to a collapse in the wave function. Because one, if you do the, for one thing, if you do the measurement uh, after the first, the wave function is already disturbed after the first measurement. And then when you do the third measurement, again, the wave function is disturbed by the second measurement. And if you do the fourth, have a wave function because it's disturbed by the third measurement, and so on. So if you only have one particle, then you should let it return to its original state before you have to measure again, because the wave function has been disturbed. So it's quite, it will take a lot of time to go back to its original state. It's better to measure many particles all with the same state, identical states, then you get the average, than waiting for one particle to go back to its original state and then measure, and then waiting, measure. So it takes time. So as time goes on, the expectation value of x is, will change. It will change because of the dependence of psi, because of the dependence of psi to the time. This is dependent of time. So the expectation value, the bracketed x, will also change because this one is dependent with time. This is not the same as this one. Not the same as this one. You have an x here, so it's now different. This is the probability the probability density, the integral of the probability density, but now we're talking about the expectation value of x, of the position. Now, how about the expectation value of the momentum? Now, this is position. First, to get the expectation value of the momentum, what is momentum, by the way? Momentum is just the product of mass of the particle times the velocity of the particle. In classical mechanics, you have that. So what is velocity? The velocity is actually equal to the derivative of x with respect to time in classical mechanics. So we can get sort of velocity by getting the derivative of x with respect to time and then multiply it with the mass. We'll get the expectation of the momentum. So again, we recall. So let me just read first the bullet. The expectation value is the average of the repeated measurements on one and exactly the same system. So it's another one system, but repeated measurement on exactly the same system. So you have to let the wave function of that particle go back to its original state. Then you have to wait and then you have to do the measurement again. Not the measurement of this system and then you immediately measure. It's not the expectation value. So recall equation 1.25. This is just the derivative with respect to time of psi, and this is the expression. If you go back to the slides, you can see that. By the way, this is just the derivative of two functions. So if you have two functions, you can get the derivative using this formula. And then this is also the integration by parts formula. So if you are integrating something, the integral would be just this. So referring to equation 1.25 and 1.28 and noting that this is equation 1.28, noting that the partial derivative of position with respect to time is 0, you will get the derivative of the expectation value of the position with respect to time to be equal to the two terms, by the way, but the first term would contain this one. The first term would contain this one, and this is just equal to 0. So that's why you only have this as an integral. By the way, the integral here is also uh, is also uh, is also from negative infinity to positive infinity. So if you get the integral of this, you get the integral of this, which is expression, this one, this is expression is just equal to this, and then you'll be able to replace that with this. You take IH bar over 2m out of the integral because that's those are constants. So you'll be left with this integral. You'll be left with this integral. Now, this can be simplified further by integration by part. This formula. Then you know for a fact that the partial derivative of something with respect to that something is also equal to 1. So in this case, you have partial derivative of x with respect to x is equal to 1. And throwing away the boundary terms as psi goes to 0 from at the infinities at the ends of are equal to 0, I mean goes to 0. So this derivative becomes this one. You set you integrate this, the f here becomes x, and the d dx here, the d over dx here becomes this one, and your g is just this one, and your dx is of course dx, and that is equal to this. So that will reduce this one, this particular expression, because here you have f equal to x, this one is x, and your g is that just this one. If you evaluate this one from negative infinity, this is just everything is 0, and if you also evaluate this at positive infinity, everything is also 0 for here. So this part of the integral, you're left with this one, so that's negative of I h bar over 2m, and then the integral from negative infinity to positive infinity of this expression. So now um, going back um, to this part, this one you can change this with the expression, or you can do another, you can distribute this integral to here, and then you can distribute the integral to here, and then do another integration by parts. So for this case, you can do another integration by parts using this one, and then you have 5 psi star for g, or you can take the integration by parts of this term also, and that's just fine, and then you will get this expression. You'll be able to get this expression. This is now the expectation value of the velocity, if sort of expectation value of the velocity. If you multiply m here, you will just to this side, and then you'll be left with so again this is the velocity, sort of velocity, but there's really no velocity in quantum mechanics. It's more significant to talk only about the position and the momentum in quantum mechanics. Equation 1.31 is the velocity of the expectation value of x. It is not the same as the velocity of the particle. Even clear that velocity means, what velocity means in quantum mechanics. So in quantum mechanics, there's only the probability of getting a particular value, not the certain or exact value. So commonly, we work with momentum in quantum mechanics and the position. So this is the expectation value of the momentum. IH bar, negative IH bar, integral of this one. We rewrite them in a more suggestive way. You can rewrite the expectation value to be this is the original expression. Expectation value of x, integral from negative infinity to positivity of x times psi squared dx. You can write it like this. Expectation value of x equal star times x. The x is now between psi star and psi. And also for the momentum, you can rewrite it like this. This expression is now at the center between psi star and psi. This is your expectation value of momentum, and the position in quantum mechanics is represented by x. And the momentum is represented by this expression, and this just a derivative with respect to space. This is one dimension, so you have x. So with respect to space, the partial differential the partial differential of the partial differential with respect to space times h bar over I is just the momentum operator in quantum mechanics. So you will be able to get the expectation value of momentum by doing this that follows it. So the operator x represents the position, and this one represents the momentum in quantum mechanics. An operator, by the way, is an instruction to do something to the function that follows it. It's not pure multiplication, but you have to operate on the function. So for example, if you have psi star is equal to x squared, then partial derivative of x squared with respect to x. So that's different from just multiplying. It's getting the derivative as an operator. Position operator says to multiply, but the momentum operator says to differentiate with respect to x and multiply the result by h bar over I or IH bar. So to calculate the expectation value, factors are sandwiched between psi star and psi, and then you integrate them, just like this expression, in between psi star and psi. So for example, if you want to get the average kinetic energy, you have this formula for kinetic energy. This is like kinetic energy is another dynamical variable. Position is a dynamical variable because it changes. Momentum also is another dynamic. You also have other dynamical variable called kinetic energy, for example, this one, and angular momentum. So for kinetic energy, you have P. This means that you have to get the second order of this one. So this becomes h bar. I square is just equal to -1. This is square over, this is or second order partial differential, and then with respect to x squared. So um, to calculate the value, the expectation value, this is just what you have to do, because p squared now from here, p, this is the operator. If the p square becomes this one, so you have to place this in between psi star and psi. This is psi star, and then you have psi here. And so h bar square would just be outside because they are constant. So this is now your expectation value of the kinetic energy. So for any dynamical variable, the momentum in that variable or the position in that variable can be changed with the derivative, and then you just retain x because x is just the same. No? So you can also get the expectation of anything if you replace that anything in between psi star and psi. Remember that psi star is just the conjugate of psi, and this psi is derived from the Schrodinger equation. Later on, don't get excited, but later on we will know how to get this psi. That's the most important thing in quantum mechanics, to be able to get this sign. Right now, we're just introducing some operation on psi and how to get the expectation values of some dynamical variables. So these are the problems that are associated with the lecture. This you can try this at home. Uh, you can clarify this problem with me on our Google Classroom or in our Mole Classroom. And these are the last few slides of the lecture. We're going to introduce to you uncertainty principle, which will be proved later on in the future lectures. No? Phenomenon, for any wave phenomenon, um, just like the quantum mechanical wave function, it's a wave, so it should have a wavelength. The wavelength of the wave function is related to the momentum of the particle by the de Broglie formula or de Broglie formula or de Broglie formula. And this is the de Broglie formula or de Broglie formula. So the momentum is equal to h bar. This is not h. This is not h bar. This is just h divided by lambda, or this is equal to 2 pi over h. 2 pi times h bar over lambda. The 2 pi here is a constant, and h bar is the reduced Planck's constant, and lambda is the wavelength of the wave, or the wave function, or the wave. And says that, by the way, before we go to that, if you have a spread in the lambda, if you have the spread in the wavelength, then that means you also have a spread in the momentum. This is a constant, by the way. So um, if this is uncertain, this also should be uncertain. If you have a spread in here, this you also should have a spread in here, because this is a constant, although this is a very small constant. Particles. So a spread in wavelength corresponds to a spread in momentum. And the general observation is that the more precisely determined a particle's position is, the less precisely its momentum is determined. That's the uncertainty principle. So if you want to determine the position, you have to pay the price by precise momentum. Or if you want to get the precise momentum, you have to pay the price of not getting the correct position. This is the uncertainty. This is the spread of x, and this is the spread of the momentum. If you go to a compromise for the spread of x, spread of p, then the product of these spreads should be equal to the reduced Planck's constant over 2. The rule in quantum mechanics. And this is called the uncertainty principle. If the spread here, is very small, the spread in momentum is very large, such that it should be greater than this. Or if the spread here is very small, the spread here should be very large, in order that this is preserved. This equation is preserved. That is called the Heisenberg's uncertainty principle. Sigma x is the standard deviation in x, and sigma p is the standard deviation in p. So I told you what it means earlier. So that's the the meaning of uncertainty principle. We will be discussing uncertainty principle more vividly in the future lectures, especially in, I guess, in chapter 3, we'll be able to know about uncertainty principle in more detail. So, um, there's a problem here that you should be doing, but I will also answer your questions regarding these problems in our Molly Classroom and in our Google Classroom. That ends for today's lecture. I hope that you'll be able to interact with me, because your interaction in the Google Classroom and in the Molly Classroom will also comprise your answers. That's the only thing that I be able to evaluate you as my students. So thank you so much, and I hope that you have a nice day ahead. The next lecture will be next week, Tuesday, mm, maybe at the same time, but I would also accommodate changing the time if you want. So we'll just talk about this in the Google Zoom. Thank you so much.